Today we're going to talk about acids and bases. To begin with, what are acids and what are bases? So acids, they're pretty well essential to the chemical industry. Sulfuric acid is actually the #1 chemical produced in the United States. It's in a lot of different items. Acids themselves are wonderful because you've got a lot of your fruits and your vegetables, they are actually acidic. So for instance, down here at the bottom you see some lemons, some grapefruit, some limes, very acidic fruits. And then down here you got these dill pickles, which are actually cucumbers that have had a little acetic acid added to them, which is the same thing as vinegar. And then you can have like Coca-Cola, which is very acidic. Acids generally they taste sour, and this is what causes your citric fruits that you see down here below. That's what causes them to taste sour. Whereas your bases, they taste bitter. Now that doesn't mean you want to go taste the most bitter base you can find, but they do generally taste bitter. The other thing that's interesting about bases is they actually feel slippery. So if you have a very basic solution, if you just kind of rub your two fingers together, you'll actually feel that your skin oil has reacted with the base, and it kind of forms like a soap that's on your hands. And so that's how you can kind of tell if your solution is really basic. And sodium hydroxide is the most commonly used base. Baking soda is sodium bicarbonate. It's probably the second most commonly used. So you've got your acids, which are your sour substances, and your bases are your bitter. But what are they exactly? So we have a couple different definitions for acids and bases that we're going to discuss today, but basically the most common thing to think about is how are they going to dissociate whenever they form inside of your liquid, inside of a water solution. So for instance, this AQ that you see right here, the aqueous stands for being in a water solution. So here we're given two examples. One's hydrochloric acid and one's sodium hydroxide. Hydrochloric acid, it's shown here in the pink solution, where hydrochloric, whenever you pour it into water, it's going to completely dissociate. It's going to dissociate into protons, your hydrogen ions, and it's going to dissociate into chlorine, your Cl- ions, your chlorine ions. And so because of that, it's given the idea, a definition of an acid, because an acid by definition is going to produce protons into solution. Your protons are your hydrogen ions. Whereas sodium hydroxide is considered a base. Why? Because, well, for one, it doesn't produce protons, and for two, it produces hydroxide ions in solution. So here you have your hydroxide ions, here you have your hydrogen ions. And that's just kind of one general definition for an acid and for a base. That a general acid, it will produce protons in solution. A base, it will produce hydroxide ions in solution. These other ions, your sodiums and your chlorines, those are just called spectator ions because they don't really contribute to the acidity or the basicity of the solution. So they're spectators. So what we have here is just two examples, one being an acid and one being a base. So this leads us to our definitions of acids and bases, where we have, for a definition of acids, we have Arrhenius, Bronsted-Lowry, and Lewis, and these are basically the scientists that work to help explain what makes an acid an acid. And so what happened here is you had Arrhenius and Bronsted-Lowry, and they proposed the first kind of definition for an acid. That is, an acid is anything that donates a proton into solution. So that's where you've got your hydrochloric example that we just looked at on the previous slide, where hydrochloric acid produces a hydrogen ion in solution, and therefore it's classified as an acid. But then Lewis came along and he said that definition is not good enough for me. He said, oh, well, I have these chemicals that are acting like acids, but yet they are not producing protons. And so he proposed a more general definition, and that is an acid is anything that accepts an electron pair. Now, why this works out really well is that if an acid donates a proton, it's also going to accept an electron pair. So that means anything that donates a proton into solution, it can be considered Arrhenius, Bronsted-Lowry, and a Lewis acid. So it can be given all three definitions. But if it's on the outer part of this circle, if it only accepts an electron pair and does not donate a proton, then it can't be called an Arrhenius acid, and it cannot be called a Bronsted-Lowry acid. But basically all these scientists are working on the same kind of idea of that they wanted to really classify what acidic behavior was based upon. And you have the one question of, is it based solely on the donation of protons, or is it more specifically interested in how electron pairs are traded in solution? And so that's kind of your difference between your two definitions. But basically you can know that if you ever have the donation of a proton, you're always going to have an acid. And there's a couple examples where if you've got a Lewis acid, then that means you're going to be accepting an electron pair. Definition of bases are very similar. So Arrhenius' definition was the first one, and so his first thought was bases are anything that donate a hydroxide. So just like sodium hydroxide, it donated, meaning it produced hydroxide whenever you put it into solution. So that was a very basic definition for that base, and so that's why sodium hydroxide is considered a base. But it also could be considered a base if it accepts a proton, and so this is kind of a more generalized statement. And so the idea here is if it accepts a proton, it could also have had an hydroxide ion to donate, or it could not have. And that's why it encompasses that central circle. But then once again, Lewis wanted to go further because he noticed that he had some bases that didn't have a hydroxide to donate and were not accepting protons, but were still acting as bases. And so he said we need to base this chemistry not on simply protons and hydroxide ions, but instead on the donation or the acceptance of an electron pair. So he classified bases as anything that donates an electron pair is a base. And so his definition encompasses every single base out there that exists. Same way for acids. His definition encompasses every definition of acid that exists. So let's look more specifically at some of these definitions. So Bronsted-Lowry, they defined acids and bases based on hydrogen ions. An acid accepts a proton, a base accepts a proton. So an acid donates a proton and a base accepts a proton. Notice also that, remember, Arrhenius they shared this definition for acids only. They did not share the definition for bases. But Bronsted-Lowry is kind of this middle definition down here for bases, and then up here we've got the middle part of the circle for acids. So acids donate a proton, bases accept a proton. Now let's look at an example. So for instance, if you throw hydrochloric into water, what is going to be produced? You're going to produce hydrogen ions and chlorine ions. Since you are donating protons, that very quickly places it as an Arrhenius or a Bronsted-Lowry definition of an acid. And water is going to accept that proton. So what happens with water, it really helps to draw out water's Lewis structure. This proton over here, this proton is going to have, if we draw its Lewis structure, remember, it's not going to have any protons. And so it's got room for protons, it's not going to have any electrons. And so these electrons the water has are going to be donated to that kind of electron hole, because hydrogen has, whenever it's an ion, it doesn't have any electrons. But it could have up to 2, right? And so what happens is water binds with the hydrogen ion in order to produce hydronium. And I'm going to spell that out for you, because really hydronium ions are synonymous with your protons. Kind of the idea here is that once you throw a strong acid or a weak acid really into water and hydrogen ion dissociates, it's going to instantly find water. And so really for you to say pH or P, you can also say your pH is based upon your hydrogen ion concentration, and we'll get to that in a little bit, but you could also base it on your hydronium ion concentration, because they're kind of used synonymously. They're going to be one and the same, because for every proton you have, you're going to produce one hydronium ion, just because it's going to instantly react like this with water. So your hydronium structure then would have hydrogen bound to oxygen. That's kind of its stick figure, where this one, either of those hydrogens could have come from the original hydrogen ion. Okay, and then chlorine's just kind of left behind as the spectator. So because your water accepted a hydrogen, so a hydrogen was bound to water, since it accepted a proton, that makes it a base. If you look back at your definitions here then, your acids are anything that donate to hydrogen. So that puts hydrochloric right here in the smack in the middle, because it donates a proton. But then also it accepts an electron pair. Come back to our picture, see how this electron pair right there is going to be donated to the hydrogen. That's what it means by accepting an electron pair. So hydrogen ions always fit into that outer category. So it's also going to be Lewis, Arrhenius, and Bronsted-Lowry. And then as far as the definition of a base, we have water, right? Did water end up donating a hydroxide ion? No. But did it accept a proton? You bet it did. So it's considered Bronsted-Lowry because it accepted a proton. Is it also considered Lewis? Okay, bases donate an electron pair. Come back to our picture. Did it donate an electron pair? You bet. Okay, so that's how water is considered a Bronsted-Lowry base and a Lewis base, but you cannot classify it as Arrhenius. Let's look at another example. So ammonia. What happens when ammonia reacts with water? So to begin with, what I suggest doing is drawing out the Lewis structures. So we have water, and then we have ammonia. Nitrogen has 5 electrons to donate, and hydrogen has 3. Well, 1 each, and there's 3 of them. So that's the Lewis structure for NH3, which is our ammonia. So what happens here? Whenever these two are connected with each other, what actually happens is this hydrogen can come in and combine with NH3 to form NH4. But why can it do that? Well, whenever water dissociates to produce a hydroxide, what's going to happen is the hydroxide ion is forming, but then also you've got your proton, remember? Well, what did protons have? It had that electron deficient region where the 2 free electrons, that electron pair on the NH3 group, can come in and fill this hole that hydrogen has. And so what it does is that allows hydrogen to be bound to your nitrogen to form NH4, which now carries a positive charge because of the positive charge on the proton. And so what really happens here is which one then is the proton donor? Water, because it gave up the proton. So since it gave up that proton, it then can form our NH4. But then NH3, why is it the base? It's the base because it accepted the proton. And so that's how you have a proton donor and a proton acceptor. And so if you go back to your other definitions that we just looked at a couple previous slides, would it be considered Arrhenius? Would it be considered Bronsted-Lowry? Would it be considered Lewis? So think about those and classify them based on this reaction that you see below. Alright, now water is kind of fun. It can act as both a base and an acid. So for water, what really makes it decide whether or not it's acting as a base or if it's acting as an acid is what is present in solution along with it. If it's present alongside an acid, it's going to act as a base. If it's present alongside a base, it's going to act as an acid. Why is that? Because it's a really weak acid and it's a really weak base. So anything that's stronger than it will overpower it and force it to act like whatever it needs it to act as. So with hydrochloric combining with water, you're going to produce hydronium and chlorine. With ammonia reacting with water, you're going to form ammonium and hydroxide. And so kind of work out those couple reactions together real quick and just kind of prove to yourself that yes, indeed, in this situation, water is acting as the base because it accepts the proton. And in the second example, it's acting as the acid because it gives up one of its hydrogen. Whenever it does this, it's considered amphoteric. Amphoteric is basically just the special name that is given to any substance that can behave as both an acid or a base. Water is really kind of the most important amphoteric molecule. Additionally, water can self-ionize. What that means is anytime you have a whole solution of water, you don't simply have just water and just water. You have instead a whole combination of liquid water with hydroxide ions and hydronium ions. All 3 of these molecules will be present in the same solution, and you have a lot of all of it. And the reason for that is because it is self-ionizing. So whenever you have 2 little water molecules coming in contact in solution, what's going to naturally happen is whenever they collide and meet, if they collide in such a way where hydrogen, which you know is seeking electrons, can come in contact with another water molecule such that it's really close to its electronegative oxygen, it's going to come off of one molecule, leaving your H3O+, forming here, and your hydroxide is going to remain behind. And so that's what makes it amphoteric and also makes it self-ionize, is that as molecules collide, they'll naturally be forming water, forming hydronium hydroxide. Then they say a hydronium and hydroxide form. They might collide and produce two waters. And so really, based on this double arrow right here, the reaction is going forward and backwards. Okay? If you look at this chart at the bottom that we've looked at before, that's why it's really important to think about all these definitions of acids. For example, water, is it Arrhenius acid? Yes, because it donates a proton. Is it a Bronsted-Lowry? Same definition, yes. Is it a Lewis acid? Yes, it is a Lewis acid. Why? Because it accepts an electron. Whenever you have hydrogen ion, remember it has that electron hole. And so these two electrons come in and fill that hole. And then what about base then? Can it act as a base? Certainly. What does it produce? It produces hydroxide. So that's in the center of the ring. It's obviously going to be all three of them. But let's prove it. So it donates hydroxide ions, therefore it's Arrhenius. Is it Bronsted-Lowry? Well, yeah. What happens if hydroxide recombines here? Okay, it's going to not only produce hydroxide, but it could accept a proton. And so that's what's going to happen here, is it's going to accept the proton from the acid. It's going to donate here. And so whenever it formed this H3O plus over here, it's accepting the proton. So at the same time as it's producing hydroxide, it is accepting the hydrogen ion. And so it's Bronsted-Lowry. Additionally, is it Lewis? Bases donate an electron pair. So if this is the base, water, it's going to donate that electron pair to hydrogen. So therefore it can be considered as Lewis. So, at the same time, water can act as both an acid and as a base. Alright, so concept check. I want you to just pause the screen right now and figure out which of these are acids and which ones are bases. And then come back through and look at the answer that we're going to talk about. Alright, so, in this example, did any of them donate a proton? We'll go with the easiest definition first. That's Arrhenius and Bronsted-Lowry. Did any of them donate a proton? Yes. Which one? Okay, if we looked on the left, this one has 3 hydrogens, this one has 2. So hydrogen was donated to HPPO4. Oh, and that's a typo. Scribble out that N. I don't know where that N came from. Okay, so it became H3PO4 because it accepted a proton. So that makes which one the acid? That makes your hydronium the acid, and your H2PO4 your base, because it accepts the proton and the other one donated our acid. So if we had to classify each of these, H3O plus would be an acid, and it can be classified as Arrhenius, Bronsted-Lowry, and Lewis. If we had to classify our base, would it be considered Arrhenius? No. It would just be considered Bronsted-Lowry and Lewis. And so you can classify it according to either of those two definitions. Additionally, over here, what we have is a word called conjugates. The conjugates are the products that are produced from reacting an acid and a base together. So for instance, now that we've formed water, this is going to be a conjugate, and our H3PO4 is going to be our conjugate as well. So what that means is we had an acid produce water, which makes H2O our conjugate of our acid, and so now it's going to be considered a conjugate to base. And our H3PO4, it was produced by our base, so we consider it a conjugate acid. And so kind of the idea is the base produces the conjugate acid produces the conjugate base. Why this is important is because if we were to turn right around and react H3PO4, it can now act as an acid. And so that's what it means, is that it's a conjugate acid because it was produced by a base, but if you were to further want to react this H3PO4, it would act as an acid. It would no longer act as a base. And so that's where the word conjugate comes from. Alright, so remember this figure. If it helps you, I recommend printing this slide off. I can put examples of it on D2L if you guys want like empty ones to fill in or big ones to fill in. But the idea here is that this slide right here, I hope, can help you classify things further. Let's look more at the Lewis definition, because I find this is the one that's most challenging for students. Remember, the Lewis definition is more general than Bronsted-Lowry. It focuses on the lone electron pairs. So acids accept a lone pair of electrons and bases donate a lone pair of electrons. So in this example, for instance, water has electrons that it can donate. Here, hydrochloric acid, so your HCl, your hydrogen is always going to have a partial positive charge, and your chlorine is going to have a partial negative charge. And so what's going to happen is your hydrogen ion is going to be forced to leave from the chlorine. The chlorine is going to take all of its electrons with it, and your proton's all by itself, remember? And it's got an electron hole. So that electron hole is filled once again by that electron pair. So your acids accept a lone pair. Is that what hydrochloric did? Yes. What about your base? Did it donate a lone pair? Yes. So your base here in this example is water. And so your new bond here is formed based on the movement of electrons. And so that's kind of what Lewis definition is used for, is for thinking about how electrons work in chemistry. If you go further in chemistry and go and take something called organic chemistry, it's going to be all about what in the world are these crazy electrons doing. And that's kind of the whole branch of organic chemistry. Okay, so concept check. How is it possible for carbon dioxide to behave as an acid when it has no hydrogen ions to donate? Meaning, CO2. Carbon dioxide doesn't look like an acid. It doesn't have any hydrogen ions in it. So can it act as an acid, or can it not act as an acid? You would think, well, every acid we've talked about so far has had protons, so maybe not. But if you're to go back at that chart and look and see, okay, we've got Arrhenius, Bronsted-Lowry, those donate a proton, but what was that last definition? That last definition was Lewis. And what does Lewis state? Lewis says a molecule can be an acid if it what? If it can accept an electron pair. And so the question is, can carbon dioxide accept an electron pair? Alright, so this is quite the fun reaction here. So this one's a little bit more complex than anything you guys will really need to get into. But this is a perfect example of what happens when something that doesn't have hydrogen reacts and to behave as an acid. So in this example, water has an electron pair and it donates it to the carbon, which has a partial positive charge, just like the hydrogen did on hydrochloric acid. And so it can accept that proton. And so then after a little bit of rearrangement, it forms carbonic acid. And so the idea here is that your water, that's going to act as your base. Your carbon dioxide is going to act as your acid because it's accepting your free electron pair. And so, can it behave as an acid? Yes, definitely. And so it can accept the lone pair on the oxygen atom of a water molecule. So anytime you have an acid, a strong acid plus a base, you're going to produce salt and water. That's called a neutralization reaction. Remember that. Acid plus base yields a salt and water. So what is a salt? This is huge. Salts are ionic products of acid-base reaction. So when you think of salts, I know you typically think of sodium chloride, but that is not by any means the only type of salt that's produced. And so what's going to happen is basically anytime you react an acid and a base together, you are always going to produce water. And then whatever is left over, you take those ions and recombine them into a salt. And so however the salt looks, that's how it's going to be formed. Okay, so let's do an example with both of these. So with hydrochloric and sodium hydroxide, you're going to form hydrogen ions, chlorine ions, sodium ions, and hydroxide ions. And that's simply because you've got hydrochloric producing hydrogen ions and chlorine ions in solution, and sodium hydroxide produces the other two. So, which of these ions is going to form to produce water? You got it, hydrogen ions plus hydroxide. Those form to produce water. So what's left over? Whatever is left over is going to produce the salt. Now the main thing to remember is you always list the cation first, meaning the positive charged species first, and then your anion, your negatively charged ion. Plus, in addition to that, you have to remember that you need to balance out the charges. So here we've got a 1-to-1 relationship. That's why we form sodium chloride. But if it were a 2+ ion reacting with 1 negative, you have to remember to balance those charges. We're going to do a little bit of practice of that here in a little bit. Okay, same thing when you got hydrochloric reacting with potassium hydroxide. Potassium hydroxide produces KOH. So your hydrogen ion would react with your hydroxide, leaving behind potassium to react with chlorine, therefore producing your salt, potassium chloride. Alright, so these neutralization reactions can happen between pretty much any acid and any base. So if you want good practice, what I really do recommend is just go find tables of strong acids and strong bases and react them together. Just practice. Form the reaction and predict what salts formed and water. So remember, acid plus a base yields a salt and water. And I've got a couple of those tables later on in this PowerPoint. Is a neutralization reaction best described as a physical change or a chemical change? Well, new chemicals are formed during a neutralization reaction, meaning the reaction must be a chemical change. Alright, so now let's go a little bit further talking about acids and bases, and let's talk about their strengths. The strength of an acid or a base is the measure of how much remains bound together as a molecule after it's added to water. Meaning, whenever we threw hydrochloric acid into water, pew, it quickly dissociated into hydrogen ions and chlorine ions. None of the original molecule, that of hydrochloric acid, remained bound together. They were just floating freely in solution. That's why it's considered a strong acid, because it will have almost no original chemical left bound together. If you would have thrown it into solution and some of it remained as the original molecule, it would be considered a weak acid or a weak base, because those have a lot more of the original chemical remaining. So here's an example we just talked about where all of hydrochloric is converted to ions. But if you have like acetic acid, which is C2H4O2, or you can also write it a couple different other ways, but acetic acid will remain as acetic acid, but it will also remain as acetate ions and sodium ions in water. And so since you still have some of that original acid molecule in water in solution, it's considered weak. Now, why do we care about this? Okay, so first of all, let me point out the difference between the two arrows. Anytime you just have one arrow, that means you have a strong acid or a strong base, and it means you have complete dissociation. Okay, if you have the double arrows, that means you have a weak acid or a weak base and you have incomplete dissociation. That means you still have some of the original reactant remaining in solution. Whereas if you have a single arrow, that means all of your reactant was converted into product. So that's kind of the difference between the two arrows. But if we look at the light bulbs here, if you stick a light bulb and you run it through pure water and then back to its battery, you'll find that with pure water you actually are not able to conduct electricity. Why? Because water is actually an insulator. If you're to throw, there's the whole thought of people used to die because you throw or accidentally drop your toaster in the bathtub. Don't know why you had a toaster in the bathtub or the bathroom to begin with, but let's say you did for some reason. Okay? If you had pure water in that bathtub, nothing would happen. You would not die, you would not even get electrocuted. Why is that? Because pure water is composed entirely of H2O as a liquid. It does not have any ions in it. The thing is our bathwater is traveling through pipes, through our faucets. It's picking up a lot of minerals, a lot of metals along the way. And so you have a lot of kind of salts that build up. What do salts can do? They have charges, so they conduct electricity. So the stronger the acid or the base, the more salts that are going to be produced that will remain in solution, the more charges that are in solution, and the more it's going to conduct electricity. So what this picture is trying to show you is that with pure water, where you have no ions floating around, water can act as a great insulator. But if you have a whole bunch of ions, it'll conduct electricity well. You'll have a really bright light bulb. But if you have a weak acid, you're going to still have a lot of neutral molecules that are going to get in the way of conducting the charge, and therefore your light bulb's going to light up still, because there are still some ions, but just not going to do it as well. Alright, so here is the chart of strong acids and strong bases I mentioned earlier. If you really want to practice doing your neutralization reactions, what I recommend doing is just pick an acid from the top table, pick a base from the bottom table, and just practice reacting them. So with hydrochloric acid reacting with, say, lithium hydroxide, what's going to be produced? Or nitric acid reacting with with barium hydroxide, what's going to be produced? Just pick one of each and just practice, practice, practice. Some of the most common weak acids that you'll find and run across are acetic acid, which is CH3COOH, also called C2H4O2, and then you also have hydrofluoric acid, which even though it does a great job of dissolving things, it's still considered a weak acid because it has incomplete dissociation. And then hydrocyanic acid, HCN. Those are your most common weak acids. Your most common weak bases that you'll run across are ammonia, NH3, and ammonium hydroxide, NH4OH. So if an acid or base that is not listed though on the strong acids and strong base table that you are given right here, assume it is weak. There are a lot more weak acids and weak bases than there are strong acids and strong bases. So here, let's practice. This is the practicing I was referring to. So if you have hydrochloric acid reacting with calcium hydroxide, the very first thing you want to do is separate each of these into the individual ions that are produced in water. So you have hydrochloric producing protons and chlorine molecules. Calcium, what charge does calcium form? You can look at your periodic table and see it's formed 2+. Or you could also uncross the charges. Also remember, what does hydroxide ion always form? A -1 polyatomic ion. Alright, so now, what is always produced when you have a neutralization reaction? Water and a salt. So, we have our water and we have our salt. So we are producing water plus, and our salt. Is CaCl right? No. Why is it not right? We have to balance out our charges. So whenever you got Ca2+ with chlorine minus, the 1 comes down here and the 2 comes down here to give us CaCl2. So our final balanced reaction is CaCl2 and water being produced. Based on these definitions then, which would you classify as the acid? Hydrochloric. It's a proton donor, so that made it really simple. What about calcium hydroxide? It's a base. It's a hydroxide donor. And so, based on these definitions here, our acid could be listed as all 3, and our base could also be classified as all 3. Alright, let's do another example. Acetic acid with sodium hydroxide. So we have CH3COOH, and I wanted to do this example to show you how acetic acid dissociates with sodium hydroxide. So what happens is with acetic acid, basically the CH3COO is a polyatomic ion and the hydrogen is the acid that comes off of it. So we have CH3COO minus and the proton and sodium ion and our hydroxide polyatomic. So first off we form water. That's our easy part. Now, what salt is formed? Sodium mixing with CH3COO. Now, do we need to, are the charges already balanced? Yes, they're going to be balanced. +1 and a -1, so they're balanced. Then how do we write it? Can we write it as CH3COONA? No. Why not? Because the cation needs to be written first. So it's NaCH3COO, and that's your salt that's produced. Now, which of these is the base? Okay, well the first key was that acetic has acid in the name, so that was the easy part. So acetic acid is your acid, and sodium hydroxide is your base. Why? Your acid produces protons, your base produces hydroxide. So, because of this then, you can have multiple types of solutions. You can either have neutral solutions, acidic solutions, or basic solutions. And an acid is when you have more protons or more hydronium ions than you do hydroxide ions. And basic is when the solution has fewer hydroxide ions, hydronium ions, compared to hydroxide ions. So if we kind of compare them, so once you've done a neutralization reaction, you can basically look to see how much of your original acid or how much base remains in solution and compare the two. If the two, your hydroxide and hydronium, are equal, it's neutral. If one is present in a higher quantity than the other, then it's either going to be acidic if your hydronium ions are greater, or it's going to be basic if your hydroxide ions are greater. So note here, your acidity, whether or not your solution is neutral, acidic, or basic, is not based on whether or not it is a weak acid or a strong acid. It's based on the number of molecules you have remaining in solution. So the more hydronium ions you have, the greater your pH, the greater your concentration will be, and therefore your lower your pH will be. And we're going to go into this in great detail in our next lesson. But just kind of note here is that whether your solution is acidic, basic, or neutral is dependent upon your hydronium ion concentration. Alright, so let me ask you this question. What do you think? Is a strong acid always more acidic than a weak acid? Or is a weak acid always more basic than a strong acid? What do you think? Think about it for a second and just write down your answer. Okay, no. It depends on concentration, aka which one produces more protons in solution. So you can have a higher amount of a weak acid to make a lower pH, whereas if you have, say, a little bit of a strong acid, it's only going to change the pH slightly, and so you're not going to have nearly as low of a solution as your weak acid. So it depends on concentration. How much of your strong acid do you have? How much of your weak acid do you have? And that's what's going to determine your pH. So to recap, today we talked about the different definitions of acids and bases, Arrhenius, Bronsted, and Lewis, and how you can use those definitions to classify compounds as acids or bases. Neutralization reactions always produce a salt and water. Strong acids or bases completely dissociate in water, while weak only partially dissociate and leave some of the original compound behind. And then acidity of a solution is determined by hydronium ion concentration versus hydroxide ion concentration, which we're going to go in depth into in our next lesson.